Okay, we can switch to the English. I think that the presentation will be in English.
Yeah, yes.
Yeah, correct. Okay, I'm very happy to introduce Daniele Visioni. Daniele is as a research associate at Cornell University. He is a climate modeler, and his main area of expertise is behavior of stratospheric aerosol and how they interact with atmospheric chemistry and with the surface climate. Among his latest publication, we can mention future geoengineering scenarios, balancing policy relevance and scientific significance, which was published in the Bulletin of American Meteorological Society. The title of the today's workshop is Climate Engineering. What we do know, what do we still need to know, and should we know it? Very, very, very intriguing. So, Daniele, the floor is yours. Thank you.
Thank you for the introduction.
40 minutes of presentation, then we can discuss.
Yeah, okay. Thank you for the introduction, and thanks a lot for the invitation. I'm very happy to be here. And as I was saying, I'm always happy to be at the intersection between climate science and the philosophy and ethics of climate science and our climate future. So I'm very happy to be here. So yes, the title is provocative. What is I'm going to try to give an overview of what we consider to be climate engineering as an umbrella term for a lot of things. But first of all, I'll try to give some context over what are our future climate change scenarios, mostly trying to explain what do we mean when we talk about future scenarios, and in particular, the Intergovernmental Panel for Climate Change definition of scenarios and how they're considered in the IPCC reports. And then I'm going to talk about the two main areas of climate engineering studies, which is carbon dioxide removal and then solar radiation modification. So to understand future scenarios, there's a lot that can be said, and there are various perspectives that one can use to understand these scenarios. This figure that I'm showing here is from the latest IPCC report, and it's what is called a burning ember diagrams. So it's a diagram that doesn't talk about what the future scenarios would be. There is no projection over the future. What this figure says is just compare to the temperatures in the present or in the past, what is the level of additional risk that there would be if the temperature keeps increasing? So there's really no projection, no timeline, no time frame for when this warming could happen, or even if it's gonna happen or not, but it's just a qualitative way to understand how risks would increase under climate change. And these are just some examples of risks, threatened systems, extreme weather events, how the impacts would be distributed, and about large-scale singular events. For instance, everyone would have heard by now about the fact that Antarctica today and yesterday has been 40 degrees above the average temperatures. So that's definitely a large-scale singular events. As you can see, compared to what we call the baseline, so the temperature in the past, there are already some risks that are starting to be detectable, to be moderate. So for instance, considering the recent temperature, so there are already risks to especially threatened systems, vulnerable ecosystems, for instance. But what we're expecting as right now we are where we are right now, where we're heading, is definitely to an increase of all of these risks and many more. So this is a way, but this is not what a scenario looks like. These are the main scenarios, on the other hand, that the IPCC defines. So as you can see, on the x-axis, we have the timeline from 1980s to 2100. On the y-axis, we have the net CO2 emissions. And the black line shows the actual emissions that we've had until 2020. And then all the other lines show possible future scenarios of how the emissions could go. And what you can see on the right is the range of possible future temperatures that will happen if the emissions go like that. So these are what the IPCC defines as scenario. And what I'd like to explain a bit is what are these scenarios and what are they for, right? So first of all, a scenario is not a prediction. So this is a thing I always use. This was probably the first prediction in climate science from Svante Arrhenius, which is a very famous chemist. And by using incredibly simple calculations, he showed that if the CO2 in the atmosphere increased by 2.5 or 3 times compared to what it was at the time, the Arctic regions would warm by about 8 to 9 degrees. And this is a surprisingly correct prediction for over 100 years ago. But it's not a scenario. It's a simple mathematical predictions. And that's what climate models do. They just use simple or not so simple equations of state to predict what the climate would be if CO2 increases. But that, again, is not a scenario. So the key thing to understand about scenarios when it comes to climate change is that scenarios always come in groups because they represent alternative possible choices or uncertainties. So it's the comparison among the scenarios that is most informative. So going back to this, if we only had one line for the future, that would be, and we claim that that was the only way in which CO2 emissions could go, that would be a prediction. The fact that we have multiple of these possible futures and we can compare between each other helps us to understand what would happen, if the emissions kept going up. Then we could have a temperature that is 5 degrees above pre-industrial. What happened if we managed to slowly bring down temperatures so that the range would be higher? So what's useful about scenarios is that they allow us to compare one another. They must also be plausible. Each scenario must at least have some sort of plausibility. It's pointless to go for scenarios that are absolutely unrealistic. But that doesn't mean that they all have to be likely. In particular, the IPCC does not include any kind of chance to any of the scenarios. So they don't say which one is more likely, but they just explore scenarios. And some of them can be very high. So we know by now that it would be very unlikely for emissions of CO2 to keep increasing throughout the entire century, mostly because doing so would require to burn 3 times as much coal as is ever been burned. And the decrease in cost of things like solar panels makes that very unlikely. But it's still possible if some parts of the climate system that we still don't understand maybe turn out to have a high climate feedback. So it's not entirely impossible. On the other hand, as what we will see later, some of the futures that assume that we can go to net negative global emissions and that we can keep the temperature down might also be unlikely, but for other reasons. But still, they're worth exploring, all of them. Another important thing is that scenarios usually have to prioritize informing the near-term decisions. We cannot make decisions now for something that could happen in 2100 in many ways, mainly because we cannot predict how the world is going to look like in 80 years. But on the other hand, we can also use near-term scenarios to understand what longer-term consequences could be. And so as an example of this, you can see here the global mean sea level change as shown. This is also from the IPCC report. And you can see that by 2100, the range of possible sea level only goes from alpha meter to 1 meter. So that's still a lot, but the difference is not as big. But then if we go sea level rise, since it depends on a lot of slow parts of the climate system, it's something that is most likely going to continue in the next centuries. So if we go all the way to 2300, and there's very little that we can do against such a projection, but it's useful. You can see that those ranges can go all the way up to 4 meters in the most pessimistic scenarios, while they can probably stay still below 1 meter in the most optimistic scenario. And finally, scenarios usually have no normative content. So they represent conditions, but representing a certain condition does not imply approval. So it doesn't imply that that's something we might want, but it's just something that we need to explore. And that brings to a lot of discussion over how these scenarios are defined in the IPCC They usually are defined through economic model, integrated assessment models. There's a lot of criticism in the literature over the assumptions that these IAMs use. But definitely what it matters for something like the IPCC is that it tries to explore different kind of forcings. And so it just asks whether it would be at least plausible to achieve those kind of CO2 concentrations that produce that forcing. And there could definitely be other ways to determine and create future scenarios, but this is the way that the IPCC uses because of a lot of reasons. But overall, what do we care about is, again, going back at the beginning, risks. So again, another figure from the IPCC report, and it shows just one of the possible risks. So hot temperature extremes, so heat waves, mostly over land. And you can see here, compared to another way to define the frequency of these events. This is a way to define this frequency. And we have that if in the past period between 1850 and the 1900, there was one chance for it to happen every 10 years. Already in the present, because of the warming that we already have, we're already at 1.2 degrees warmer than the pre-industrial period. This heat wave is 2.8 times more likely to occur. If we stay if we stay at 1.5 degrees or 2 degrees, and those are the thresholds that were defined in the Paris agreements that were signed in 2018, this heat wave is going to be 4.1 times more likely, or 5.6. And overall, if we go all the way to 4, this will be 9.4 times more likely. So this is why we care about scenarios, not as a way to try to predict the future, but to try to understand how risks are going to change. And so now I'm going to try to focus on this part. So the one that says 1.5 degrees. Again, the Paris agreements that were signed by mostly every country on Earth, they pledged, well, every country pledged to try to do as much as possible to keep temperatures below 2 degrees above pre-industrial by the end of the century, and possibly below 1.5 degrees. So we're only 0.3 degrees in terms of global mean temperatures before we reach the first of the two Paris Agreement thresholds. And the reason why that was signed is because, again, risks were defined, and staying below threshold that we already overcame, like, it's pointless, but 1.5 is there. However, what then the countries asked, and they asked this to the IPCC that produced a report on this in 2018, was what would it take to stay below 1.5? So what would be necessary to do to actually make sure that temperatures do not go above this dangerous threshold that we define? And when I say threshold, it doesn't mean, I'm not talking about a hard limit over which we all go extinct, but we're talking just about a normative threshold that we define. And we know that risks are going to increase above that threshold. They're going to increase more if we go above 2, and more at 2.1, and so on and so forth. So that this number, this 1.5, this global mean temperature, is just a proxy for actual risks, for actually a cascade of risks. So this figure that is updated from the 1.5 report asked what would it look like, what CO2 emission would look like if we were to stay below 1.5. And the black line, again, is the current emissions. The green dot is the 2021 emissions. And these all these blue filaments, all these blue lines that you see, are possible future scenarios under which we manage to stay below 1.5. As you can see, there are many, but the most obvious glaring thing of them all is that almost all of them require for the curve to go below 0. So there is this shading area, this shaded area, this brownish area that says net negative global emissions. And basically that's the truth that is beyond the 1.5 report, that based on IPCC scenarios, the only way that we actually have to stay below 1.5 degrees is if the global CO2 emissions not only reach 0, but they actually go net negative. So we have accumulated enough CO2 in the atmosphere up to now that it's basically going to be impossible to stay below a threshold that the whole world, every government in the world decide as safe, and above that it would be unsafe. But to do that, we need these negative global emissions. And what do they mean? So another way to look at the same figure as before, this is from a National Academy of Science, the US National Academy of Science report, is in this way. So we have a certain amount of emissions, and we're trying to mitigate. So the main thing, the main work that we need to do, the main job throughout this century is to mitigate these greenhouse gas emissions. But that's definitely not going to be enough. There's a part of greenhouse gases emissions that are what we call hard to abate. So there are emissions that are incredibly hard to abate without basically abandoning our current way of life. And I mean, even just concrete, even just producing concrete to build houses produces a huge amount of CO2 that is very hard to abate by normal techniques. So we assume that conventional abatement technology, so reducing emissions by, for instance, switching to all technologies to all sources of energies that don't burn fossil fuels, can do most of the job, and it has to do most of the job, but it's not going to be enough. Part of that we can mitigate with reducing emission technologies, but that's still not going to be enough. So we need a bit of the part of the shaded blue area, which is negative CO2 emissions that are carbon removal technologies. So technologies that manage to somehow directly remove CO2 from the atmosphere in order to go back at levels, in order to, first of all, or compensate the emissions that we do not manage to abate, but then also to reduce the legacy emissions. So the CO2 that has been in the atmosphere, that is in the atmosphere already, has been emitted in the past, and that is going to stay there for hundreds of years unless we do something like that. So there are plenty of these carbon dioxide removal methods. And the main issue with them is that, and this is the first time where the term climate engineering comes in. So we can assume CO2 emissions are not a form of deliberate modification of the climate. CO2 emissions are just a byproduct of our society, of the way our society has evolved during the last 200 years. But for most of the time, first of all, we weren't aware, and now we're not in a way capable to reduce the CO2 emissions. So the climate change that it produces, the climatic changes that it produces are not intentional. Removing the CO2 and doing other things, on the other hand, is physically going to change, deliberately going to impact the system in many ways. So, and these are just some examples of carbon dioxide removal techniques. Some people divide them between natural methods and artificial methods, but in many ways, that's not a useful thing because those are still things that are going to affect the system in a different way. So, and again, we can go from the right, there's afforestation, reforestation, and improved forest management. So one of the main sinks of CO2 is, well, one of the main one is the ocean. The other one over land is definitely vegetation. By photosynthesis, it can trap the carbon from the CO2 and store it underground. So one could say if we plant more trees, there's a lot of coverage for these 1 trillion trees to plant and so on. That's a way to increase the land carbon sink and make sure that more carbon is stored in plants. We can increase soil carbon by tilting the soil in a certain way, by adding some products to the soil. There's biochar, there are more artificial methods, so direct air CO2 capture. So we physically take the air from the atmosphere, we pass it through some chemical thermodynamical processes, and we remove CO2. It's very hard, it's very energy expensive, but there are some pilot projects around. Chemical weathering and so on. These are over land. There are even more. This is another report from the National Academy of Science from this year, and there are all the ocean-based methods. So there's seaweed cultivation, ocean alkalinity enhancement. Now, I'm not gonna list them all because there's really plenty, and every day that someone comes up with a different method. But the fact is that there are plenty of issues that as soon as you start looking into these carbon dioxide removal methods, start to arise. So, and what are the main issues? Now I've tried to list them here. This might not be conclusive, and it's also the way I see it, but it's just to give you an idea. So first of all, none of these carbon dioxide removal technologies are risk-free. And this is not obvious at first glance, especially if we go back to this one. people might think that afforestation, so planting a trillion trees, is a non-harmful way to help climate change. But when you start digging into it, the main question starts to be, where are you planting these trees? What was in the land where you're planning to plant these trees? So of course, reforestation and improving forest management could be much less harmful, but they're also not that effective. Whereas planting trees where trees are not, where didn't used to be, it actually is something that comes with risks of its own. And all the other techniques, we can do that for all other techniques. So that's when the precautionary principle comes in. The precautionary principle says that we should not try, well, one way to interpret that is to say that we should try to minimize risk as much as possible. So doing something that is not proved, that is not tested, and it might have risks in the future, something we might want to avoid. Another main issue that comes with these kind of approaches is that, and a lot of critics say this, is that even just talking about them distracts from reducing emissions. If we imagine that we can remove the CO2, we might be less compelled to reduce our emissions fast enough. And then if for some reason these technologies don't scale up, they don't actually work, then we're left with more emissions than we actually would have had otherwise. The other issue is that who would be in charge and how much do we need? In the figures that I showed before, again, here you can see that the blue area is 20 gigatons of CO2 per year towards the end of the century. And now if you look at the emissions that we have now, those are like around 45 gigatons of CO2 equivalent per year. So we're basically saying that by the end of the century, we need an amount of removal that is almost half of the entire production of CO2 of the world. So that is definitely something of a scale that right now we can't even imagine. It's like imagining to substitute most of the production in the world and turn it into its opposite. Who benefits locally is also another question. This is a question that already comes up a lot with renewable energy. If you propose to have a gigantic solar farm, the question that comes in is, what is the benefit to the local community? Especially if it's a technique that may come with risk or like pollution, then it becomes even more important to ask this question: how can the community discuss and be part of the decision process? And finally, and another thing that is actually scientifically probably the hardest of them all, is how can we measure progress? Right now, there are very few methods to directly measure CO2 emissions from various kind of industries. Most of the numbers that I showed in the figures before, those are always either self-reported or bottom-up esteem. So you estimate how much CO2 is being produced, and then we see the amount of CO2 in the air. But that takes time to build up. In the same way, it's very hard to be sure that somebody claiming that they're trapping a certain amount of CO2 are actually doing that. The ways in which we can understand that are incredibly complicated. So there's a huge issue with accountability. So zooming in on just a few of them, one of the ones that it's incredibly interesting to talk about is this moral hazard question. And a lot of people thinking about the ethics of it. That's one of their main concerns. But actually, and this is just a figure that I find incredibly interesting, when you see, if we look back, if you look back here, and we see that the amount of negative emissions that we need already by 2040 starts being greater than zero. So that's less than 20 years away. But when you actually go and look at the amount of investments that are in carbon dioxide removal technologies, that is incredibly small. So these are all the climate tech funding since 2020. And you can see that it's of the order of like $10 billion. And this tiny part over here of way less than $100 million is carbon. So it is about technologies that remove carbon from the atmosphere. And similarly, if you look at it from the energy, and even then, this number is a tiny, minuscule number compared to the investments that we're seeing for energy transition. So for now, it appears as if the worry is never about the amount of money that would be spent over investing over CDR technologies, but more about the way in which we talk about it. Looking at some more specific issue, as I was saying, each one of the CDR approaches that are discussed, they all have some kind of a specific governance issue or some ethic question that comes with it. So this figure is from the C2G, the Carnegie Climate Governance Initiative, that puts together a lot of these schematics, and I find them very useful to explain a bit. So one could artificially encourage the growth of carbon-absorbing plants in the ocean, but how would that affect the marine environment, and how can we study that? We can mass plant forests, but what happens to the people that need that land to grow the food? When we talk about this Trillion Trees project, and you actually go and see where their simulations of the future plant most of these trees, it turns out that they always plant it in places where people, especially in the south, are growing food. But food is needed. Food is way more necessary in many ways. So how can you reconcile building these trees in places where they didn't used to be and growing more food, because we are going to need more food? And the same could be done for each one of them. How can we scale them up safely? Do we even know if it will work? And in terms of land, in terms of ecological, there's plenty of these issues. So when one looks at this, and it's clearly that right now there's no CDR, no carbon dioxide removal at scale going on, and there are plenty of doubts over where that's feasible. So the question is, do governments know what they're talking about? You might have heard there's a lot of every once in a while there's the announcement that a new country has come up with a pledge, or like a net zero target, what's called a net zero target. A net zero target is where it's when a country says, by 2050 we will be net zero, which means that the same amount of CO2 that we will still be emitting will also be removed through maybe these kind of methods. And the reason why a lot of the times we hear also that, and the last IPCC report said this as well, we might not be headed to a catastrophic scenarios with 7 degrees of warming by the end of the century. But also when we talk about what the pledges bring us, we have to remember that a lot of these pledges, a lot of these policies consider in themselves a lot of negative emissions. And here, this is from the Climate Action Tracker, and I find it a very interesting figure here, because it kind of says that no country has an acceptable net zero target. So they all have targets that heavily rely on these future technologies that are not proven right now, and that there's a lot of questions over the scalability. But most of them, even especially the biggest one, they either have an average or poor judgment. They're really not that great. So clearly, the governments are making use of this concept of negative emissions to produce net zero targets that they can claim will bring them to zero emissions by usually 2050. But how about people? This is another very interesting figure. The fact is that while governments kind of use this term broadly of negative emissions at these for these net zero targets, usually people have never heard about the issue. So sometimes over 70% of adults have never seen, read, or heard about carbon removal practices, between not much and nothing at all. And of course, when you ask people then if they support expanding the use of carbon removal practices, of course, they always say, most of them say that they either strongly support, somewhat support, half of them say that they support them. Most people don't really have an opinion, and very few oppose them. But this is interesting because this is very generic. But when you ask actually people whether they want carbon dioxide removal projects in their community, then these numbers change a lot. But mostly they're just not informed. So a lot of these questions, when a lot of these polls actually ask people things that they know nothing about because they haven't been informed, not because they are to blame, but because they just haven't been informed. And this is an interesting, again, following poll where people are asked, what are carbon removal practices? And they sometimes manage to define them pretty good, but they say that recycling, for instance, over 70% consider recycling a carbon removal practice, and it is not. or renewable natural gas or geothermal. Those are not carbon removal practices, and yet people consider them as good carbon removal practices. But for most of them, the ones that actually we suppose that should scale up, most people haven't heard of them. So bit of midpoint, well, a bit more than midpoint. It is very likely that we're heading for a global warming that overcomes most of the Paris Agreement thresholds, so 1.5 or 2 degrees. And most, if not all, governments' pledges rely on carbon dioxide removal a lot for net zero. So a lot of the pledges that say we can keep at least warming below, 2 degrees, they rely a lot on this concept of net zero, and they rely a lot on carbon dioxide removal. But we don't know, we really don't know, and we need to know a lot more, but we really don't know if carbon dioxide removal would work at the scale that we need to make those net zero pledges be true. And finally, that these issues are mostly absent from public discussion. So where do we go from there? Where do we go from here? So we have this knowledge of the fact that we're already seeing risk from climate change. We're very likely to see more. And that most of these negative emissions that would allow us in the at least medium to long term to reduce these risks are still a big question mark. So we are probably headed to a point where already by 2040 we might already see temperatures go above this Paris Agreement defined threshold. So is there something that we could do in the even shorter term to make sure that we don't go above this threshold? And here's where solar radiation modification, or again, climate engineering or geoengineering comes in. It is defined as the deliberate modification of Earth's climate through the reflection of a portion of the incoming solar radiation in order to reduce some of the risk produced by global warming. This is the IPCC definition. And here on the left, you can see a schematic of how these solar radiation modification, or SRM, methods would look like. So the idea basically is we cannot do anything in the very short term to fix the problem that we created with CO2. So can we slightly reduce the amount of solar radiation incoming to slightly cool the planet so we know we're not getting above those dangerous thresholds? And there are a few methods that have been proposed in the past and in the present. Increased scattering by including stratospheric aerosols, thinning high clouds. There are these high wispy clouds that sometimes we see at mid latitudes that actually they don't cool, but they warm the planet because they trap outgoing long wave radiation. So if we reduce them, one can hope that they would allow for more long wave radiation to escape and cool the planet. Or we can increase the scattering by low marine clouds that cool the planet a lot, and we know that because we see with ship tracks do that. So those are the main methods that have been proposed in the past. Would they even work? Well, for some of them, we have some ideas that they would indeed. This is a figure of globally average surface temperature, and what you see in red here is big volcanic eruptions in the past. So these events, Krakatau, Santa Maria, Gung, El Shishon, and Pinatubo was the last one in 1991, are all events where explosive volcanoes erupted and they launched a huge amount, and talking 20 teragrams of SO2 directly into the stratosphere, and that produced a measurable cooling for the following years. So in 2006, so people did talk about this before, but the thing that kickstarted this idea of using possibly sulfate to slightly cool the planet comes from Paul Cruzen, who won the Nobel Prize for basically single-handedly with Mario Molina discovered the ozone hole over Antarctic and basically saved us all through spearheading a lot the effort to avoid a world where the ozone hole grow bigger. And in 2006, he wrote this paper, Albedo Enhancement by Stratospheric Sulfur Injection, a contribution to resolve a policy dilemma. And he said that, well, the article is very nice, very easy to read, but it basically says, if the reduction in greenhouse gas emission will not happen fast enough and the temperature will keep growing, this form of climatic engineering may be the only option available to rapidly reduce temperature rise and counteract other climate effects. Maybe they could be stopped at short notice, but we definitely need to know more, because it is possible that if the positive effects are greater than negative effects, these might seriously have to be considered. And he introduces a lot of caveats. He's not proposing that we do anything like that. But he said from his perspective of someone that already helped save the world, this problem that we have in temperatures maybe could be solved like that. So very briefly, what stratospheric aerosols this sulfate would do when the sulfate gets to the stratosphere, which is the part above the gray line, which is the tropopause, the troposphere. Below here is where we live. It's very turbulent layer. Nothing that you put up stays for that long. But above the tropopause, above these threshold in altitude, the stratosphere is a part of the atmosphere that is very stratified, as the name says, and things stay there for quite a while. So when we put SO2, which is a gas, when the volcanoes do that at least, it produces these particles, these sulfuric acid, tiny liquid particles that are usually alpha micron in size, and they are exactly the perfect size to reflect part of the incoming solar radiation. And that's what volcanoes do. They stay then for 1 year or two, and in that period we can measure, and we have with cases like Pinatubo, that indeed it did cool the planet. So we have an idea that it would work. And even when it comes to, well, let's talk numbers. I say 20 teragrams, or here is in thousands of gigagrams of SO2, and that number doesn't really mean anything to anyone. But actually, we already emit a lot of SO2. We emit a lot of aerosols from the surface, and this figure is the SO2 that is emitted by humans through various processes from starting in 1850 all the way to now. And you can see that there's been a huge increase because they are produced in a lot of ways. Mostly coal combustion produces SO2, but petroleum combustion does as well. Metals melting, there's a lot of processes that produce SO2. The fact is that these SO2 and that the aerosols they produce stay in the troposphere. They stay very close to our head, so they fall back down very quickly, and so they don't manage to cool the planet enough. And they're also pretty harmful in terms of health issues. And here you can see that even if we put ourselves in a case where we try to offset 5 degrees of warming, the amount of SO2 that would be needed to put in the stratosphere based to climate models and calculations, so there can be variations, but based on also what we observe from volcanoes, is definitely a fourth of what we currently emit from the surface. So if we manage to clean up our surface emissions, we would definitely be in a better place. And it's roughly the amount of SO2 that was emitted in the 1930s. So this is all in terms of course, bare technical feasibility. It could be that it would work. But then that's not enough. So that's not the only thing that we can ask. The main question is, as Paul Cruzen said, what are the risks and what are the positives of something like this? So, and it really, to answer this question, really depends on what are we comparing against and what are we putting ourselves. So here on the left, you can see the projected surface temperature increase in a world that has much higher CO2 concentrations than now. And you can see that, temperatures rise almost everywhere. This means that precipitation changes. This is from projection from climate models. And then on the right, you can see what would happen if we offset all of this warming using one of these techniques, again, from climate models. And it's clearly not perfect. This is very important to understand. Overcoming CO2 forcing is not the same as reducing solar radiation at the top of the atmosphere. So it wouldn't be perfect, but and I always repeat that obsessively because it's important to understand, in our climate models and based on our understanding, it would do actually a efficient job at reducing temperatures, but it would have other effects. So for instance, here on the bottom right, you can see what would happen to precipitation. And it would change precipitation in an opposite way than climate change does. So there are, as you can imagine, lots of risks that need to be evaluated. This is a perspective that we wrote last year. And again, there are plenty of things. For instance, ecosystem impacts. We know that definitely on the left, imagining to use any of these forms of climate engineering to completely offset the temperature increase from high emissions is not a good idea for a lot of reasons, because there's a limit to how much CO2 we can put before it really starts being more dangerous than we want to put from the surface, because then we would need to be committed to do it forever, mostly. And if we stop, then suddenly we very quickly go back to where we were before. So clearly not a good idea to imagine as one of these climate engineering techniques as perfectly capable of helping us avoid reduced emissions. But we can imagine one of these proposals as a way to help us. So if we cut emissions, but we don't do that enough, we do some CO2 removal, but that's not enough. It's not easy to scale that up. Can we use stratospheric aerosols to cool back down and to achieve one of the temperature targets that we think are safe? And of course, then the question is, who controls the global thermostat at that point? Who decides, aside from the CO2 increase or decrease, who decides how much engineering to do, how much climate engineering to do to cool down, and what do we cool down to, right? So that's a important question. And also what we find from the research that has been done up to now is that definitely putting the aerosols up in the atmosphere, it is not like turning up or down the thermostat, because the aerosols mix in a complicated way, because it depends where you inject them on the effect that they have. So more than a thermostat, it looks like a control panel, but not a control panel that we know perfectly well how it works. More like a control panel that we're blind to, that we maybe have a vague idea how it works, but we have no real idea to how to focus to control it for real. And so again, the main question that would come if we ever were to consider such a proposal is, what would the cooling target be? We say 1.5 because we've decided that there's no way we stay way below 1.5, and 1.5 is probably the only threshold that we could perhaps reach. But what if that's not enough? I mean, why would we have to stop at that point? If we know we can cool, who gets to decide whether we stay at 1.5 or we go cooler than that? And we've been exploring this a lot. This is some work that we've been doing right now. And we can imagine that different countries, different populations, different societies, different interests might decide, if we were to be able to actually directly influence the temperature of the planet, we might want to not just limit ourselves to a Paris Agreement temperature threshold, but we might actually want to cool back down the planet even more. And what would that do? Here there are some metrics that we came up with. So stratospheric ozone, what would happen? We could probably recover sea ice. Is that important? Is that not important? What would countries that live in the Arctic that now are trying to exploit the fact that they can navigate some routes year long would think of more sea ice rather than less sea ice? What would happen to the oceans? What would happen to the circulation? So there are plenty of things that, even when you put yourself in the framework for something that is mildly possible, a lot of issues that come up. And again, the main issues with SRM are the same ones that I showed with CDR. Who would be in charge? Who benefits? How do we know it's working? But there are a lot more that need to be touched upon when thinking and discussing SRM. Do we even have the right to do it? What's our relationship with nature, and do we really have the right to directly influence temperature? What about if that produces an increasing conflict because countries disagree? So there's an international relationship problem. How does that interact with climate justice issues? Again, who gets to be heard in the decision process? How do we attribute extreme events that are due either to climate change or to the intervention? And there are even more that probably we haven't thought of yet. So definitely, and I'm concluding here, there are what the framework we need to put ourselves in is one of determining risk, but not just risk on the road. So what is the risk of doing something versus the risk of not doing something? What happens if we decide to do or embark on the road that leads us to deliberately modifying the climate, versus what happens if we don't? What happens if we don't manage to reduce emissions, and so climate change just happens? So as a conclusion, and of this second part, not claiming that solar radiation modification or any form of climate engineering is a solution to climate change. It doesn't treat the underlying causes, does not fix all problems, and is imperfect, at best, if you're lucky. However, as we move towards temperature threshold that we scientists deemed safe, the question that we will all be faced with, and decision maker will be faced with, is doing any of these things safer than not doing them? And they are already there. They're already in these questions are already in some of the reports, and they will soon be, or they already are, parts of mainstream climate policy. So there are questions we need to be ready to answer. And the thing that I'm mostly concerned about is that even more than for climate change science, this issue of interfering with the climate deliberately asks for much tighter collaborations between climate scientists and social scientists, because new methods of governance will be necessary. And it's pretty obvious that we can do this very wrong, but it will be very, very hard to do it right, if at all. And I'm done. Thank you for your attention.
Thank you for your very, very interesting presentation, and stimulating also. I have a very general question. I'm a little curious about the general approach to this question from your discipline. Also because we started recently a new PhD program on climate change and question-related climate change, which is an interdisciplinary, deeply interdisciplinary project. So, from your perspective, which is obviously the perspective of a climatologist, what do you think that which disciplines do you think that must collaborate in order to face the question of climate change with some possibility to reach some points or some conclusion? Because as you underline often in your presentation, it's a multidisciplinary perspective. So we have to use different devices, different instruments, different point of view. Which are the most important one for you?
So there are basically almost every discipline throughout this century is going to come up with the question of, well, except except particle physicists. But every other discipline is going to come up with this question. And to me, the most important thing, and one of the things that the IPCC is also now highlighting, is really this issue of how do we make this transition to a livable climate, a sustainable society, but how do we make it just? So, and how to make that just is an incredibly hard questions, because again, there are themes like more ethical themes, but that are really incredibly interlinked with the science. So for instance, how much can we ask for developing countries? How much can we ask them not to emit if we have already emitted? So, and if we have definitely benefited in the past and in the present from unabated emissions, and most of the CO2 that is now in the atmosphere is CO2 that we, as in Europe, the United States, and in smaller parts, China have put up. So how can we ask developing countries in Asia and in Africa to not do what we did? And this question is not just scientific, because we can say we can do technological transfer, but how to do that, and how are their society is going to look like? So there's a big issue for me of how just do we want to. It's probably a transition to an economy that doesn't emit too much, or that is as close as possible to net zero, is not that hard to do in general, but it's hard to imagine how to do that in a just way. And to do that, it's going to require a lot of expertise with local communities. So broad philosophical questions, how much can we ask and what should we be asking? But also a lot of question over what is necessary in terms of international relationships or relationship within countries that benefited from something versus the one that are actually now mostly feeling the impacts of our past decisions. So there's a lot. So to me, that is the most interesting thing. How do we make sure that different kinds of communities are heard, and that whenever we make, and even when I say we, even just the word we, using it like that, is a problematic word in many sense, because who am I talking to when I say we? Who is the decision maker? So who are the decision makers, and who controls these decision makers is an important, incredibly important question. So really, it's going to require
so if I understand correctly your point, if you put aside scientific question, we have a lot of ethical problems in terms of justice and points like that. But in order to face a question of ethical questions, which are obviously mainly philosophical, especially philosophical point, is enough for you to use scenario, which were the instruments the line you draw at the very first part of your presentation, or we have to provide some prediction? Because obviously, if we go to a prediction, we move from a plane, which is a scientific one, to another, completely another plane.
Mm-hmm.
What do you think?
So yes, we definitely have to rethink how we think about scenarios, for sure. What I said at the beginning about the fact that these scenarios that the IPCC comes up with are non-normative. They're not telling anyone what to do. They're just telling what happens. It definitely lacks the nuance of understanding that people are waiting for, well, mostly scientists, considered in the broad term, to answer the question of what actually do we need to do. So, and probably this way of defining scenarios from a completely technocratic point of view is not the right way to go. So we definitely need to think, how do we make new scenarios that are significant? Because then there are scenarios that can really inform what should we do in the future. But how do we make those scenarios relevant by not making them just, the output of a model that is maybe clear, maybe open source, and maybe not? But how do we really make that process a participation between a lot of different actors?
Thank you. Francesco? Do you want?
There is Elena first.
Something? Okay.
So thank you very much for the presentation. I've learned a lot, I think. And am I allowed 2 questions? Okay. So my first question is, in order to apply SRM, we should give up with any precautionary principle. Is that correct?
If you consider only, it's a very good question, in the sense that what does the precautionary principle looks? The issue is with how does the precautionary principle looks like when we're already headed towards something. Here we're not discussing to modify the climate to something we like more. Here we're more asking, can we avoid some risks that we already know are going to happen? Right. So in this perspective, there is definitely a precautionary principle that says we shouldn't do something that we don't know how risky is going to be. But we also are now, and that's another one of the main points that of the IPCC, we are heading towards growing risks from climate change. Some of these risks we simply don't know. One of the reasons, so there are long-tailed risks. So what if there's a risk we haven't foreseen for climate change because we've never lived, because society as it is now has never lived through a climate with much higher temperatures and much higher sea level rise. So those are risks. On the other hand, deciding to do something about it in a way that actively interferes with the climate also comes with its own risks. So the precautionary principle, to me at least, it should be and it's one way to frame it. It should definitely be applied considering the risks of doing it versus the risks of not doing it. And then, and again, how to decide that, that's the main question, right? So it's, it could be that the risk of doing it it's much, much higher. It could also be that that's not.
Yeah, because I was thinking, for instance, when you think about the GMOs, you know, the precautionary principle is more interpreted in the sense that since you don't know the output, then it is better not to do it. And
Right,
I was just comparing. In that case, I mean, you may say, okay, GMOs can help in fighting hunger in the world. Okay. Yeah, but I realize it's not exactly the same.
It's not the same also because it would be a much easier question to answer if we were proposing to do something for which we have no natural analog, like GMOs.
Yeah.
The issue, the thing that makes it hard is that we know there have been volcanic eruptions in the past, and we know that the world survived and thrived. There were some local issues. Of course, I'm not saying that volcanic eruptions are not dangerous, but we know what happens, right? So, and I'm not, this is not a value judgment for me in saying that it is safe, because it's not the same. But it's just an observation and makes it harder because we really cannot say, oh, this is something that has never been tested before, and therefore we should steer clear of it as much as possible. This is a question. We know that there's the possibility, because we've seen it happen in the real world, that this worked. So if this worked, could we do it again? And it could very well be that the answer is no. Really not saying that the answer is going to be yes. But there's the possibility. And so the fact that that possibility exists, does it mean that we have actually a moral duty, at least to study it for future generations? Well, that's it. And I'm not talking about far removed in the future. I'm talking about the next 30 years. So if we reach the 1.5 thresholds and we see that there are some huge risks in the tropical regions, and we have never even tried to study techniques that could mitigate those risks, are we doing a good service or not? And I really don't have answers to those questions.
And here comes the second question, because we know, for instance, that volcanic eruptions, cause like mass extinctions in the past, right? So my question is, does climate engineering work together with ecologists?
So for the first part of your questions, the reason why there have been past extinctions that are maybe volcanoes contributed is because they were at we were talking about extinction. We call them extinction level events. We're talking not Pinatubo level. We're talking about hundreds so yes, those exist. But if something like that were to happen now, and it doesn't look like that's possible, but if something like that were to happen now, there's just simply nothing that we could do against that. So, but your question is excellent. We do, yes, the one of the papers that I showed before in the perspective we have in PNAS is actually with a group of ecologists that we've been working with very closely in the last 2 years. And the idea was really to put together a group made of, in a tiny part, climate scientists, but in a large part, ecologists that had never heard about climate engineering at all, and talk through it with them. So we gave presentations, explained the issue. And at the beginning, the reaction was, this is absolutely crazy. Why are you even talking about this? But then thinking through it, you can really, the moment you frame that, not just as, oh, we're going to save the world, but as, could these reduce risks and could these avoid the extinction of ecosystem for which there's no turning back? Because if we go above a threshold, we could suffer, we could have risks, but overall we could adapt at the end. But there are ecosystems that cannot adapt. So for ecologists that are preoccupied with ecosystems that are at the verge of extinctions, then the question really becomes, we should at least consider it or not.
Thank you very much.
Welcome.
Francesco?
Thank you, Daniele, for your presentation. I learned a lot and it was extremely informative. I have two clarification requests about distinction between predictions and scenarios, because in addition to methodological differences, does the point of this distinction lie in more in the expected accuracy of predictions and scenarios respectively, either in their expected informativeness for policymakers. I mean, perhaps comparing contrasting scenarios is more informative for policymaking than a single prediction, however accurate the latter might be. This is the first clarification request. The second is about the distinction between the likelihood and the plausibility of a scenario that you touched upon in your presentation, and I think is worth expanding on a little bit.
Yeah, so for the first one, it's an excellent question, but the main issue and the reason why the IPCC tries to be so very clear over the fact that there's no prediction mostly has to do with how lay people and the public understands them. So, and again, because the hardest part, so one could say that, we're trying always to improve climate models and so on and so forth, but basically the physical basis is there. We know that if we put more CO2, the temperature is going to increase. What we cannot predict, because it's literally impossible to predict, is how society is going to develop in the next decades and what's that going to mean for CO2. So if we say that, so the distinction that we try to make is between, we say if emissions are going to go up, this is what will happen to temperature. But that is not a prediction, because a prediction implies that we know what emissions are going to look like. So this is why we have to span across a large range of scenarios, because the risk is that, and there are a lot of people that also try to think through and decide what scenarios are more likely. But really the main issue is that the public always ends up understanding what a projection as a prediction, and that's incredibly harmful for the future when that projection that was not a prediction turns out not to happen. And I'll give you an example. Maybe this is confusing, so I'll give you another example. Let's talk about COVID. And there's been a lot of discussion, especially in the UK, in the US, with in the UK with scenarios for COVID spread that the Imperial College came up with. And there were some worst case scenarios and best case scenarios. And all of the time, there was always a worst case scenario. And the journalists and newspapers always said the Imperial College is predicting that there's going to be 2 million cases per day. Whereas what the Imperial College was saying is that if we don't do anything, we're going to have 2 million cases per day. And just by saying that that's the worst case scenario, people's behavior changed, and it made the worst case scenario less likely. But then what happens is that at the end, when the worst case scenario didn't happen because people were warned and people changed their behavior, then newspapers go back and say, oh, that prediction didn't happen. And so the scientists themselves are discredited, even if what they were only trying to do was to warn over the worst case scenario. So this is mainly a problem of communication, right? Of not of what's true and what's not, and what we can make our best judgment, but over how the people that are outside the process understand these kind of warnings and these kind of scenarios. And for your second part, so that might have been not entirely clear, but so when I say plausible, I really mean something that is physically plausible. So again, we cannot right now, without carbon dioxide removal, go back to a pre-industrial temperature in the next 50 years. That is just implausible. Even just imagining, like, there are some wild scenarios that say in 2040, suddenly we're going to have 50 gigatons of CO2 less per year in carbon dioxide removal. We know that's not going to happen. We physically know that it would take a miracle, and we don't know, none of us deal in miracles. Likelihood is another thing. So we can say that it's very unlikely that carbon dioxide removal will scale up to 20 gigatons per year. It could still happen because we don't know. Maybe there's a scientific breakthrough that we don't know about, and that's going to make it likely. But again, it's a very small likelihood. And it's the same for when we talk about business as usual. So 5 degrees, 7 degrees of warming. We know that most likely people are already doing that, and people are going to stop using coal because the amount of coal production is already decreased. And we can assume that that's going to continue because prices of renewables are going down. But what if there's, I'm not, okay, it sounded a lot better when I said it, when I used to say it 2 months ago, but what if there's another world war and we get thrown back 50 years in the past, and so we have to go back to using coal because our technological development gets stopped by a catastrophe of any kind, right? So it's unlikely, but still something that is worth thinking through from a risk management perspective.
Thank you so much, Daniele. I would have 2 more questions, but I leave the room for other possible questions from other participants, if any.
Okay, I can ask other question. Otherwise, Francesco can add his points. We can finish, by the way, with this more question raised by Francesco, if you want.
Should I go on then?
Yeah.
Okay. Okay.
Yes.
One of the 2 additional questions is just something I'm curious about. It is, to what extent, if any, are fossil fuel companies actively engaged as sponsor of carbon capture research? Because I was thinking that successful carbon capture technologies would enable fossil fuel companies to take part in facing climate crisis so as to prevent an implausible short-term phase out from fossil fuels and to allow a more plausible gradual decarbonization process. So I was wondering whether and to what extent are they actively engaged in financial support of these research and development projects. And the second question is about something you just touched upon in your presentation, which is nuclear energy. And I was wondering if you can add something more about the role that nuclear energy can play in decarbonization scenarios. Because I was wondering, are we still in time for employing nuclear power as massively as it would be needed for it to count as a game changer in the decarbonization challenge? Because public opinion is, of course, a key variable for nuclear energy to be politically viable. But a debate has been reopened recently, in Italy at least. And so I was wondering whether you have something to add about this.
Okay, so for the first one, yes, and it's very complicated, but fossil fuel companies say they actually talk a lot about net zero. They are the main player that talks. They always say net zero now. They even announce something like carbon neutral fuels. The fact is that they don't usually mean CDR in most cases. So they don't actually mean, their investments in actual carbon dioxide removal are very small because they really have no interest and it's very expensive. What they usually talk about are either carbon offsets, which are, I didn't talk about them, but they're like another whole mess. So you pay someone to offset your emissions by doing something, maybe in the future, that will reduce those emissions, that will cancel out those emissions. And another thing that they use a lot is what's usually called CCS, so carbon capture and storage and utilization. So the idea that you suck CO2 out of the air, you pump it in already used oil digs, and that allows for you to extract more oil. So technically, that means that the oil you extract has a lower footprint, but it's not zero. And also, however, as you were saying, that kind of helps these companies stay afloat. So there's a huge issue of the fact that these companies are really trying to force this net zero. All of these companies will have a net zero plan. All of whether they're state-owned, private actors, all of them have a net zero plan and talk a big game about net zero. But what they actually do is really a massive effort in delay. There's no doubt that whenever companies talk about this, there's a huge issue of delay. On the other hand, I will say, so there's a lot, as I was saying, if you look at those curves that I showed, and they show that basically we would need an amount of removal that is equivalent to what we're emitting now, or half of that, there's a question of infrastructure and of expertise. So fossil fuel companies don't just extract fuel, they do a lot of research, geological research. And so they do have, it's true that they do have the expertise. I mean, after all, it was scientists paid by fossil fuel companies that first rang the alarm about climate change. Then the fossil fuel companies hit that, but it's true. They have a lot of expertise. So there's a huge question in the transition of how do you make sure that you don't have the companies profit from that, but also don't waste the incredible amount of expertise that they have when it comes to carbon dioxide removal in particular. So it's a really huge issue, and I have no recipes for that. But this idea that fossil fuel companies can just disappear in the span of 10 years, it's incredibly unrealistic. But not because we don't want to, it's because the infrastructure that is out there right now, it's so huge and gigantic that we really wouldn't know what to do without that, without fossil fuel companies. So probably their expertise, there's a lot of arguments that can be made that their expertise is still going to be necessary. But also it's true that they are playing a delay game because they don't want the transition to happen as fast as possible. For nuclear power, well, so again, the issue is that the risks that we're facing are now, they're not in 50 years. So this question would have sounded a lot different 50 years ago. And the world went the way it went for a lot of reasons. Some of them were good, some of them bad. There were Chernobyl, Fukushima. So there are some, in a way, good reasons why parts of the world shied away from nuclear power. Some of the reasons are also not that good. But the fact is that right now we are in a place where a lot of the countries are actually closing down or phasing out nuclear power plants. And Germany, for sure, is one of them. The United States in many ways. And there are a lot of countries that just have never had that much nuclear power to begin with. And so the fact is that building new nuclear power plants is going to be slow. It's very slow. And if you stop learning, there's a lot of learn by doing in nuclear power plant building and development. So it is so nuclear power is gonna play a smaller role, especially in the next 20 to 30 years. And there's really no way around that. We can wish as much as we want, but the fact is that also most people are really incredibly opposed to that. And sure, public opinion is feeble, but it's not that much, because in Italy the answer has been consistently for 50 years that Italians don't want, for instance, nuclear power. So it's not something we can rely on to save us from climate change now. And again, we can talk going back 50 years, what would have happened, but it hasn't happened. So I find it at this point a bit pointless to keep bickering over whose fault was it that we didn't have nuclear power. It happened, it didn't happen. So we have CO2, and if we build a nuclear power plant, if we start now, even if you imagine only 5 years of decision making in deciding to build a new power plant, a nuclear power plant, and then it's another 15 years before you build it. So that's 20 years. So we would already have been above 1.5 by then. So if, we should keep the nuclear power plants we have as long as possible from a world perspective, but I don't think we should rely on building new one. And when it comes to nuclear fusion or that kind of tech, the joke is always that it's been 70 years that nuclear fusion is 30 years away. And it's still, if you ask nuclear fusion people, they will still say that it's 30 years away. So, in the long term, I hope that we crack nuclear fusion and that we are really able to live in a world that is fossil fuel free for good. But it's not what I'm focused on right now, what we should be focused on right now.
Thank you very much. I think that we can stop here. Grazie, Daniele.
I have one question.
The very last one.
Very last. Okay, these kind of technologies are, you said that they are expensive, right? Mm-hmm. And they use energy, correct?
Yes.
Yeah. So how can you produce that energy without, if you have no nuclear power, and how can you produce it without using other fossil fuel.
Yeah, that's a big issue. So the few pilot direct air capture plants that exist are all in countries that have more energy than they need. So for instance, Iceland, because they have a lot of geothermal, Switzerland, because so yeah, actually so when it comes to direct air capture, there is really no way to solve that problem, because they're always going to take more energy, a lot more energy than, and energy, we don't yet have free energy, so that energy could be used for other things. So it's true. If we had nuclear, and even when it comes to nuclear, we don't have that much to waste. So it's a big issue with direct air capture, that it's very unlikely that it can be done at scale, because it takes insane amounts of energy.
Okay, thank you very much.
Thank you, Daniele. We learned a lot, so it was a pleasure to follow your talk.